So far on this channel, we've used Shadergraph a lot, but we've avoided talking about shader code. Things get a bit more complicated when using code because there's a lot of background stuff you need to be aware of, but I also think it's useful knowing how pure code shaders work at a basic level, even if you only intend to use Shadergraph. In this Unity Basics video, we'll see how writing shaders with code works in URP. Remember to subscribe to catch these videos in the future, and check out my Patreon if you want early access. We'll start by going to the project view, right-clicking and selecting Create, Shader, Unlit Shader, and then name it whatever you want. I went with Example Shader. When you open the file up, you'll be greeted by a lot of boilerplate. We're actually going to select everything between CG Program and NCG and delete it. This template code is designed for the older built-in renderer, but we want to set up our shader to use the shiny new features of URP. We're left with comparatively little code. This is written in a language called Shaderlab, which is a Unity-specific shader language which bridges the gap between Unity and quote-unquote real shader code. In the first line, we can name the shader by changing what's between the double quotes. This name defines how the shader will appear in the Material Inspector shader dropdown, so for me, it will appear under Unlit Example Shader. Next up are the properties. These act the same as Shadergraph properties, and they're variables which we can use in the shader, but also modify within the Unity editor. Currently there's only one, and the syntax goes like this. Its name is _main_text, and the name we'll use in the inspector is texture. Its type is texture 2D, and by default, we want it to use a completely white texture. We will see a few more types of property later. Then we have a subshader. A single shader file can contain several subshaders, one after the other, and the first one which can run on the hardware will be picked, although I very rarely use this cascading behaviour of subshaders myself. Inside a subshader, we have tags which define when and how the shader is rendered, and the LOD level, which can be increased if this shader is particularly demanding. You can force Unity to fall back to shaders with an LOD level below a certain threshold. Finally, we have a pass. During a single shader pass, Unity will render the object that this shader is attached to once, according to whatever shader code we've written. However, we just deleted all the shader code, so of course nothing will happen yet. This is where we're going to put back some of the quote-unquote real shader code of our own. In URP, we use a shader language called HLSL, or Higher Level Shading Language. If you've written shaders in the built-in pipeline in the past, you will have likely used CG instead of HLSL, but this is the quote-unquote proper way of doing things now, because URP's core libraries are written in HLSL. Now that we know which language we're going to be using inside the pass, I can stop saying quote-unquote real shader code and things will hopefully go a bit more smoothly. So, how do we start writing HLSL? We need to tell Shaderlab that we are changing to HLSL, and there are two different ways of doing that. Just above the pass, we are going to write HLSL include and end HLSL on separate lines, and between these, we are going to set up the things that will be used inside our shader pass. We can define more than one pass, and everything between the HLSL include block will be available to all those passes. To start off with, we will import the standard URP shader library. It's a pretty long line. We need to say #include packages/com.unity.render-pipelines.universal/shaderlibrary/core.hLSL with the capitalization I put on screen. This file contains a bunch of stuff that will be very helpful for the many shaders we're going to write. Now we will deal with properties. Again, we've declared properties at the top of the file, but we need to include them a second time in HLSL. In URP, it's a bit different to the way you might have handled properties before. We declare a container for the properties called a cbuffer between cbuffer start and cbuffer end. We give it the special name Unity per material, which ensures that these properties will be the same for every shader pass. It might seem strange that we need to put all these inside a buffer like this, but that makes our material compatible with the SRP batcher, which, to oversimplify massively, makes rendering happen faster. Inside the block, we redefine all the properties we had before, but using their HLSL types. It's a bit annoying, but you've got to do it. We're going to add another property at the top of the file first. I'll call it _baseColor, give it a name, baseColor, its type is color, and the default value is 1111, which corresponds to white because the red, green, blue, and apple values are all full. Now inside the C buffer, we write float4 _baseColor. Float4 is HLSL's type for RGBA colors, although really it's just a 4-element vector. Float4s don't necessarily have to be colors. Textures are special and don't need to go inside the C buffer. We need to define the texture and a sampler that we can use to sample the texture. We do that by saying texture2d _mainText, then sampler _mainText. The name of the sampler is the same as your texture, with the word sampler stapled to the front. That's a lot of setup, but you get used to it quite quickly. For a lot of my shaders, I just copy my previous work and change the bits that aren't boilerplate. Now we can write some shader behavior. When we talk about shaders colloquially, we are usually talking about the overall combination of everything inside this shader file. On a deeper level, shaders are usually made up of a Vertex Shader and a Fragment Shader. We're going to deal with the first one first. I mean, that makes sense, right? Starting at the beginning. The shader starts by receiving data from Unity. Not just the properties, there's more that we need to handle, such as vertex positions and UV coordinates, which Shadergraph handles for you invisibly. The Vertex Shader then operates on every vertex of the mesh, of the object that the shader is attached to, and typically places the vertices in the correct positions on screen. We write a struct to contain data passed as input to the Vertex Shader. Sometimes the struct is called attributes or app data, but I prefer to call it vertex input because it's input to the Vertex Shader. Our shader isn't very complicated at all, so all we need here is the vertex position and the UV coordinates. For that, we can say float4 position and float2 UV. HLSL also requires us to add what are called semantics to those variables so that the shader compiler knows what each variable is intended for. The position variable uses the position semantic, and the UV uses text coord 0, which is short for texture coordinate. We also need a struct containing data output by the Vertex Shader. You could call it varyings or v2f, but I prefer vertex output. I'm sure you can guess why. We will be outputting a position and a UV coordinate again, so we will say float4 position with the sv _position semantic, and float2 UV with the text coord 0 semantic. sv _position is slightly different from before, and it means pixel position. For both these structs, make sure you remember the semicolon at the end. Now we can write the Vertex Shader. We've actually written everything we need inside HLSL include block, so now we can finally talk about the second way to declare HLSL code. Inside the paths, we will write HLSL program and end HLSL, and here we can write our Vertex Shader. It's a C-like function, so we put the return type, vertex output, then the name of the function, vert, and a list of parameters. We'll specify a vertex input named I for input. Inside the function, we'll declare a vertex output called O for output, and we're going to populate each of its members one by one. Here, we need to transform the vertices from object space, where each vertex is positioned relative to the model zone center point, to clip space, where each vertex is positioned relative to the 2D screen coordinates. Unity provides a function for this. It used to be called Unity Object to Clip Pos back in the built-in render pipeline, but in URP, it's now called Transform Object to HClip, into which we pass the vertex input position and assign it to the vertex output position. You might get warnings back in the Unity editor about implicit truncation, and to make those disappear, just use .xyz. Then we can just say o.uv equals i.uv because we don't need to do any special transformations for the UV coordinates. Now we can write the Fragment Shader. This is sometimes called the Pixel Shader because these image fragments are usually the size of 1 pixel. After the Vertex Shader is complete, HLSL takes all the triangles that are visible on screen and turns them into fragments in a step called rasterization. Our Fragment Shader will operate on every pixel and return a color as a float4, which is the final colour of those pixels, and it takes a vertex output as its only parameter. We need to give the function itself a semantic called sv_target, which is a bit different to the vertex shader, which doesn't need one at all. Inside the fragment shader, it's fairly straightforward. We can sample the main texture at the correct UV coordinate by using the sample_texture2D macro and passing in the main texture, its sampler, and the UV coordinate specified in vertex output. As we mentioned, colours are just float 4s, so this gets assigned to a float 4 called base text. To mix colours together, we can just multiply float 4s together, and HLSL will multiply each element one by one and return a new float 4. So if we want to combine base text and _base colour together, and return that as the final colour in one fell swoop, we can just write return base text times _base colour. Awesome, that's the fragment shader completed. We just need to tell HLSL that these functions are the vertex and fragment shaders by saying #pragma vertex vert and #pragma fragment frag. And then if we assign this shader to a material by selecting unlit example shader from the shader drop-down menu, we can start to assign textures and change the colour to see changes. This tutorial should give you enough base knowledge to get started with an extremely basic unlit shader, but if you're looking to take things further, I've linked a few things in the description to get you started. There's the Unity documentation, although since the scriptable render pipeline's launched, it's been a bit harder navigating the split documentation, so I've linked a relevant page. Cyan also has a brilliant guide for getting set up with URP shaders. He goes further than I do here, so it's well worth checking out. This video was made possible by those wonderful people who support me on Patreon. Check out my page if you want an exclusive member role on the Discord or early access to videos. Or if you want to support me with a one-off coffee, my Ko-fi is there too. Please, I live on coffee, I'm begging you, I need it to make more videos. Unity Basics will return in the future. I've got a few ideas jotted down and am currently eyeing up either interpolation, 2D physics effectors, or creating custom post-process image effects in URP. Or maybe it'll be something completely different. My mind moves at a mile a minute. Until next time, have fun making shaders.